Talking about integration. Move into this other half of calculus and a lot. All right, baby step it. See how far we get before Christmas. All right. Thanks. No day off. All right. The indefinite integral. We are starting with integration. You will be able to apply antidifferentiation to the indefinite integral. And I'm just going to go ahead and be 100% honest with you. I looked at how much stuff we have left and how much time. And if we are doing exams, then, which they have not made the call yet, whether or not exams are going to still go forward or if it's just going to be like how it was last year and just be the IA. So my goal is to kind of keep going, pushing forward. So I'm going to kind of cut out some of the theory part of integration just to make sure I can hit what would be covered on the exam. However, if they do give us the word that it's going to be strictly your IA, then I'll go back and kind of cover the theory part a little bit to enhance maybe some IAs who might need to use integration in theirs. Okay, right now I'm basically going straight into it. So I'm avoiding like the whole fundamental formal definition part of integration and just going like straight into it. Okay, so because there is one. If you want to know, ask A and I. All right, they did it today. But the antiderivative of x to the n of any power type function is given by the formula 1 over n plus 1 times x to the n plus 1 plus c. Okay, where c is an arbitrary constant and n does not equal -1. If n did equal -1, well then we would essentially not have any type of variable and it would be undefined for the leading coefficient, which we can't have. Okay, c is an arbitrary constant that can become a specific type of constant depending on other information, but in general for the indefinite integral, there's indefinite, you're going to use plus c. Okay. So in other words, what you're doing is you are doing the reverse of differentiation. So now it's like you're given the derivative function and you're asked to find the original function. And to do that, all you do is you add 1 to your exponent. Okay, that's how you end up getting 3 as your exponent. And then you do 1 divided by the new exponent, which would be 3. So the original function, if your derivative was x squared, is 1/3 x to the 3rd power plus c. Do not forget your plus c when you're dealing with indefinite integrals, okay? You can always check your answer by doing the derivative of whatever you get, okay? Because if I do the derivative of this, remember derivatives when you bring down the exponent, you multiply and you subtract 1. Well, 3 times 1/3 is 1. 3 minus 1 is 2, and what's the derivative of a constant? 0. So you got x squared. So you can always check your answer going that way. This is, again, like the power rule for integration, okay? So we're going to find the antiderivative of each of these functions. These 3 we're going to do together, then I'll give you 6 to do on your own. Again, you want to add 1 to your exponent, so that's going to become x to the 11th power, and then your coefficient is going to be 1 over the new exponent, which will be 11, and then you can't forget about your plus c.
Never forget.
Never forget, okay? Especially for indefinite integrals. So it'll be 1 over 11x to the 11th power plus c. When I look at B, okay, again, that rule that we have is for powers. Right now, this is saying 1 over x to the 5th. I can't quite apply the formula right now. I'm going to have to rewrite this so that it is in the form of x to the n power. How do I do that? I would do x to the -5. Then I would apply that rule so that I can do the antiderivative, okay? Add 1 to your exponent. What does that become? And then your coefficient is going to be 1 over the new exponent plus c. But of course, we cannot have any negative exponents, so how do I make that exponent positive? You bring it to the denominator. So this is actually negative, because it doesn't matter whether the denominator is negative and the numerator is negative, the entire fraction is negative. It'll be a negative 1/4 x to the 4th in the denominator plus c, and that will be our antiderivative. When we look at c, I have the 4th root of x to the 3rd. Again, this is not a power function yet. I'm going to need to rewrite that. The 4th root of x to the 3rd can be rewritten as x to the 3/4 power. So then I can apply the rule. Now that it's a power, I add 1 to my exponent. What's 3/4 plus 1? 7/4. Then I do 1 over my new exponent with my plus c. Now, of course, we can't leave a fraction within a fraction. So what's 1 over 7/4? It'll be 4/7. And that is your antiderivative. That's how you apply the power rule and find the antiderivative of these functions.
Would it be okay if we turned the x to the 7/4 power back into a root?
Then that is totally fine. You can definitely change this into the radical form. So that'd be 4/7. What root would it be? It would be the 4th root of x to the 7th power plus c. Just make sure that you put the right root. Remember, your denominator is always your root. That is also acceptable. Try these 6 on your own. Try these 6 on your own. So applying the power rule, what is going to be number 1?
Like the answer?
Yes.
1/8 x to the power plus c.
Very good. Remember, you add 1 to your exponent. Your coefficient is 1 over the new exponent. What about for the next one? Not x plus c.
Oh, wait.
Negative 1 over x plus c. Yes, because when you add 1, that gives you an x to the negative 1. Then this is technically just the negative 1 in front because it's 1 over negative 1. So then you got to make it positive. Good. What about the next one? Very good. Number 4.
I said 3/4. Wait, I'm yeah, 3/4 x to the 4/3 power plus c.
Good. Next.
Number 5. 3x to the 1/3 plus c.
Very good.
Negative 1 over 3x to the power like the x plus c.
Never forget the c. Questions? All right. So antidifferentiation is also known as the indefinite integral, and it's denoted using an integral symbol. Okay, this is derived from Riemann's integral, which again, that's like that part of that theory that I'm leaving out here. Okay, when you see this symbol, that means you need to perform antidifferentiation. Okay, so this black printed symbol, that is the that represents the indefinite integral. dx is the variable of integration, and it's always a part of the actual integral symbol. So anytime you see the integral symbol, you'll always see dx or dt or du, depending on what the variable is. It's going to be d something. Okay, so for example, you have the integral of x to the 3rd dx. This essentially would be what is given to you. When you see that, that would mean perform antidifferentiation. So you would use the power rule, where you add 1 to the exponent, then your coefficient is 1 over the new exponent plus c. All right? So if capital F prime of x is equal to the original function f of x, then what we can do is we can write this using the symbol, the integral of f of x dx. F of x, the function that you're taking the antiderivative of, is known as your integrand, is equal to capital F of x plus c. Again, your constant of variation. Pretty much what's on the slide here is just the notation part that deals with the antiderivative. So again, when you see that symbol, it means to perform the antiderivative. And again, you'll always see the integral symbol with a dx or a dt or a dy, depending on what the variable is in the problem.
So as long as we get the symbol as close as possible to that,
You're
we're
fine. Yeah. Okay. It's like it's an extended S. Okay. It's not a normal S. Don't do that. Extend that middle part to form that integral.
What is the sloppiest one we can do?
Okay. So again, when you see that symbol, that means you're doing the antiderivative. There are a few rules that go along with the indefinite integral. Okay, all of these are very straightforward rules. Of course, you have your power rule, which is what we just did. Okay, you have the integral of x to the n dx. That is 1 over x plus 1 times x to the n plus 1 plus c. Of course, n cannot equal -1. You guys have that one written down already. These other three, though, straightforward, slightly common sense. You have the constant rule. The antiderivative of any constant k dx is equal to kx plus c. So anytime you have a constant that you're taking the antiderivative of, it's always that constant x plus c. So if you see the integral of 15 dx, what's the antiderivative of that? 15x plus c. Because remember, you can always take the derivative of 15x and you will get 15, the original function, right? Okay, that's the constant rule. The constant multiple rule says that if you have a constant times a function, dx, or you're taking the antiderivative of a constant times a function dx, what you can do is you can pull out the constant outside the integral symbol and then just take the antiderivative of your function. So what does that look like? Let's say I have 2x squared dx, the integral of 2x squared dx. Well, 2x squared is technically my function, but I have a constant of a 2 in front of that x squared. So I could pull out the 2 and then just do the antiderivative of x squared, and whatever I get, I multiply it by 2. What's the antiderivative of x squared?
3x.
Not 3.
Oh, sorry.
So then it becomes 2 times 1 over 3 x to the third power that gets multiplied by that 2, then plus c. Do not multiply your constant by any, don't multiply your c constant by any k constant that you pull out.
So your K and your C numbers touch.
Correct. So then that would be your final answer, 2/3 x to the third plus c. All right. Lastly, of your simple, basic, straightforward rules of indefinite integrals, you have your sum or difference rule. That's basically saying that if you have multiple functions that are connected by an addition symbol or a subtraction symbol, you can essentially just take the antiderivative of each individual function. Okay? So an example of that would be something like if you have the antiderivative of x squared plus x plus 1 dx. Essentially, you're just going to take the antiderivative of x squared take the antiderivative of x, then take the antiderivative of 1 separately, each individual piece. And then you get your answer. Of course, don't forget your plus c. So it wouldn't be 3 individual answers. It'll be that one answer, all the antiderivatives plus c. So that would be 1/3 x to the third plus 1/2 x squared plus, what's the antiderivative of a constant? It's self x. So the antiderivative of 1 is 1x, then plus c. That would be your antiderivative of that function there. I'll try to avoid this corner because I know that stuff's blocking right there.
Oh, okay. That makes sense.
All right. I want you guys to try these 5. Try these 5. Find the indefinite integral. Okay? Do be aware. Remember that dx, that dt, that dx, that du, that dx, that tells you what the variable is inside the problem. So when you take the antiderivative of it, you want to make sure you use that respective variable. So use your different rules along with your power rule and find the antiderivative of these 5, a through e. All right, here we go. We're finding the indefinite integral. We have the integral of x to the 6th dx. That becomes what? Get your plus c. Very good. That's just your basic power rule. What about b? 4t plus c, because the variable is t, because it was the dt. Yes, that is a constant, so you just add the variable onto it. Wonderful. That's your constant rule. What about c?
1/2 x to the 6th.
1/2 x to the 6th power plus c. Very good. That is your constant multiple rule. If you pull out that constant, you take the antiderivative of x to the 5th. That becomes 1/6. X to the 6th. That gets multiplied by the 3, and that's how we get 1/2. Constant multiple rule there. What about the antiderivative? What about the integral of 3u to the 4th plus 6u to the 2nd plus 2 du?
3/5 u to the 5th plus 2u to the 3rd plus 2u plus c.
Never forget the c. Very good, especially on an indefinite integral. That is your constant. No, that's your sum and difference rule. And then for your last one,
1/2 x squared plus 3/4 x 4/3. Plus c, plus c.
plus c. Never forget the c. Always gotta remember that plus c at the end. Very good. Okay. Yes, all of these are your pretty straightforward, basic ones, just involving your power rules, your basic other rules of integration. Okay. Now, do realize that whenever you put a plus c at the end, you're finding a general solution. Okay, because realize that that constant changes that original function that you're finding the antiderivative of. Okay, so that's known as a general solution when you just take the antiderivative and you put the plus c at the end. Okay, but let's say you're given some additional information about this particular function that you're taking the antiderivative of, such as the position at time t equals 1 is 6. Okay, the position. Think back to when we were doing derivatives and things like that. Position represented what? What was another word for position? Well, kind of your y value, but I'm looking for a different name.
Is it something related to vectors?
Not vectors. It's good though, because we did talk about position. Think motion, linear motion with the derivatives. When we talked about the position of an object, that represented its
Location.
Velocity?
not velocity, but you're in the right ballpark. Not acceleration. Go the other direction. What was the original function called? Because velocity was the derivative and acceleration was the second derivative. What was the original?
Isn't it just like position?
There's another word for position.
Oh my goodness.
Speed.
Not speed. That's involves derivatives. Okay. Another word for position was displacement.
Ooh.
Okay? Displacement was your original function S of t. Okay? And so if it tells you that the position at time t equals 1 is 6, well, essentially what they're giving you is they're giving you your x coordinate and your y coordinate, time and position for this particular object, or this particular particle that's being represented by this equation. So what you can do is you can actually use that additional piece of information to find a particular solution for C. And so all you do is once you take the antiderivative of your function, you will plug in 1 for t, 6 for s of t, because that's your position after 1 second. And you find that your constant specifically is 4. So given that additional piece of information, you're actually able to find a particular equation for that function that you're taking the antiderivative of. Okay? So yes, don't ever forget your plus c when you're doing the antiderivative. But if you're given some additional information, then that means you need to actually use that to find c and actually find the specific equation. Okay? And we're going to do that here with this example. It says if f prime of x is equal to 3x squared plus 2x, and f of 2 is equal to -3, find f of x. This is what I was talking about when we're doing derivatives, integrations going backwards. I give you the derivative, now you give me the original function. Okay? So to do that, you do the antiderivative of that function, 3x squared plus 2x dx, and you take the antiderivative of that. Give you about 30 seconds. What is the antiderivative of 3x squared plus 2x?
X cubed plus x squared plus c.
Very good. This is a general equation for f of x when you have that plus c involved. But you're told specifically that f of 2 is equal to -3. So we actually are able to find the original function by plugging in -3 for f of x and 2 for x to solve for our constant. And then we'll actually have the original f of x function. So that's going to be -3 is equal to 8 plus 4 plus c. So c is going to be equal to -15. So our equation is going to be x to the third plus x squared minus 15. And that's how we actually find the original function. Let's look at this next one. It says a curve y equals f of x passes through the point 32, 30. The gradient of the curve is given by f prime of x is equal to 1 over the 5th root of x to the third. First off, don't forget, what does the gradient of the curve mean?
It means the derivative.
It means the derivative. So even if that f prime of x was not included, you need to remember that the gradient of the curve indicates the derivative. Because even though I know it doesn't say it here, I guess I must have forgot to finish off the rest of the question. You have to find the original function, okay, where the gradient of the curve is given to you, and you also have a point that passes through, okay? So find my original f of x function, okay? Just a reminder, you have to take the antiderivative of the derivative function given to you, and then plug in the point for x and y to find your c, okay? So I'm gonna pause the video. I want you guys to do that. So we do the antiderivative of the of the derivative function. So I'm going to go ahead and rewrite that as x to the negative 3/5 dx because I have to apply the power rule because I haven't learned any of the other rules yet. So I'm applying that so that way I can find the antiderivative, which you get to be what? Okay, so that is your general solution. But because we are told that x is 32 and y is 30, we can plug 30 in for y. 5/2. I'm going to go ahead and rewrite this as the 5th root of 32 squared. So then that way, since I don't have a calculator, I can a little bit easier do this algebraically. The 5th root of 32 is squared is, and when I multiply by 5/2, I get, so then c is actually going to equal 20. And because of that, my function that represents this particular situation where the antiderivative is 1/5 root of x to the 3rd and passes through that point 3230 is 2/5 x to the, is 5/2 x to the 2/5 plus c. All right, 2 more. You want to do this one on your own. See if you can take the words, decipher what they mean, and actually find the number of fish at t equals 4 years. The rate of growth of a population of fish is given by dp over dt equals 150 square root of t. Remember, when you see dp over dt, that's like saying dy over dx, aka the derivative. For t is in between 0 and 5 years. The initial population was 200 fish. Initial population means when t is, okay, so you have a coordinate here, 0 to 100. And then you're asked to find the number of fish after 4 years. So to do this, one, we need the equation that represents the population of fish. So then that way we can figure out after 4 years how many fish we actually have. So what you should have done is you should have done the antiderivative of 150 t to the 1/2 dt. I used 1/2 because I had to convert that square root. When you did the antiderivative, what did you get?
100 times 3 to 3/2.
Very good. That is your general equation to represent your population of fish. We need to figure out our specific one, especially since the initial population was 200. You should have plugged in 200 for P of t and found that t was equal to, I'm sorry, not t, c was equal to 200. It will not always be this way. It really just depends on the original function that's given to you when you take the antiderivative. All right? So then our specific equation that represents our population is 100 t to the 3/2 plus 200. So then all I need to do is plug in 4 for t. Again, another non-calculator problem where I take the square root of 4 to the 3rd power. And to be honest, sometimes it's easier to apply the root than the power. So how many fish do I have? Oh, I thought you said 800, not 1,000. I'm like, wait, what?
12 fish.
I was gonna say 100, 900,000 or something.
All right. All right, last but not least, we're gonna find the original function given that we're given the second derivative as 12x squared minus 4, but we know that f prime of 0 is equal to -1 and f of 1 is equal to 4. Now do realize that the second derivative does involve acceleration, okay? And then since we're given that f prime of 0 is equal to -1, that's basically telling us that the gradient when x is 0 is equal to -1. You know, that's what that f prime of 0 equals -1 means, okay? And then the original function, f of 1 is equal to 4. This information can be represented differently. You just have to be able to remember that certain things mean the derivative. Certain things mean the original function. Because like I said, instead of giving you this part right here, they could have said that the gradient is -1 when x is 0. Then you would have to realize that, oh, that's a point that I can plug in to help me figure out the constant for the first derivative, okay? So to do this, I'll do this one with you. we're going to take the antiderivative of the second derivative function, okay? When I take the antiderivative of the second derivative, that's going to give me the first derivative. So 12x to the second, that is going to become 4x to the third. Accidentally touching stuff. Minus 4x plus c. Double check behind me, is that right?
Hold on. 4.
Yeah, that's right.
Yeah.
So that represents f prime of x. Okay? So to find c, that particular constant, I need to use that information that f prime of 0 is equal to -1. So I'll plug -1 in for f prime of x. Then I'll plug in 0 for my x's to find out that my constant is equal to -1. So my first derivative was 4x to the third minus 4x minus 1. And then
You gotta find the antiderivative of that, don't you?
I have to find the antiderivative of this. I repeat this process to actually find the answer that they're wanting me to get, which is the original function. So I take the antiderivative of the first derivative. That's going to give me x to the fourth minus 2x squared minus x plus, technically I could use c here because I've already figured out what the first c was, but to be honest, use a different variable to represent the constant for the original function. Okay, use a different variable. Does it matter what variable? No, but c and k are usually the common ones for constant. That's why I use k instead of a different variable. So then how would I find constant k?
You plug in 1.
4.
Equals 4. You plug in 1 for x, so everything equals 4.
You plug in 1 for x and set everything equal to 4 because of this piece of information that we're given there. So then that'll give me 4 equals 1 minus 2 minus 1 plus k. So k is going to be equal to 6. So my answer, my original function, where the second derivative was 12x squared minus 4, and I had all that other information about the first derivative and the original function, is x to the fourth minus 2x squared minus x plus 6. Okay? So you can do it as many times as long as you're given information. And to be honest, even if I wasn't given that information that I've underlined in blue with a squiggly line or the squiggly line in red, even if I wasn't given that information, I still could have found an equation for my original function. It just would be a general one. Okay, so yes, instead of here for the coefficient, instead of it being -1, it would have been cx. And instead of 6, it would have been k, a different constant. Okay, so if you're not given the particulars about the original function or the first derivative, you can still find a general original function. You just would have variables to represent those coefficients for those constants. But that is your first little bit, introduction-wise, into integration. You have your power rule, you have your constant, constant multiple, sum and difference rules, and you have your way of actually finding out your constant. But if you don't, you need to find your constant. Don't forget your C.